Okay, so chapter 8, this is essentially our last chapter. We're going to do one topic from chapter 9, so there won't be like a chapter 9 assessment by itself. It'll just be in with chapter 8, so this is kind of our last section. We're in the final stretch. Don't worry about these ones. There's different ones at the bottom. We are going to just do this in one day, so don't worry about day 1, day 2. So our first section of chapter 8 is the integral as net change. And so we've done some of this, just not all of the applications. Chapter 8 is very application based, so very much like real life applications of some of these things that we've been doing. What situations might we want to add up the area under a curve or those sorts of things. So some typical examples of net change include how far an object traveled or where the new position of a particle is. So if we have a velocity graph, we can add up all of the area underneath, those sorts of things. We will find this using the velocity equation and knowing how much time has passed. This works really well if velocity is constant. If it's not, then we can figure out the area under that curve either using a Riemann sum, so that's the RRAM, LRAM, or MRAM, Simpson's rule, trapezoid's rule, the function of integration on our calculator, or by evaluating the integral. So any of those options are ways to add up that area. So suppose a particle's velocity is given by the equation v at t equals 6 sine of 3t between 0 and 2 pi. Okay, so when is the particle moving to the left and when is it moving to the right? If we think about this, if the thing is moving to the left, if we've got velocity and time like that, if we have a positive velocity anywhere up here, that means it's moving to the right. If we have a negative velocity anywhere down there, it's going to be moving to the left. So basically, when 6 sine of 3t is greater than 0, this thing is going to be moving to the right. And we can figure out what t has to be in order to do that. So if we divide both sides by 6, okay, so now if we look at the sine of 3t has to be greater than 0, this is a hard thing to solve, right? We don't know, because we don't know what t is, we can't multiply it by 3. When we have that 3 in there, it makes things tricky. So what I'm going to do is I'm going to replace it. So I'm going to go sine x has to be greater than 0. So basically what I've done is said let x equal 3t. Because now, if I think about this logically, if I'm just talking about a single angle x, I know where this thing is greater than 0. I know based on my unit circle from Math 30, 1, 0, that sine is positive anywhere between 0 and pi. Okay, so 0 is less than x, which is less than pi. That's where sine is positive. Okay, so if we replace that 3t in there, so 0 is less than 3t less than pi. If we divide all of that by 3, we end up with our boundaries for t. So 0 has to be less than t, which has to be less than pi over 3. Okay, to the left, we're looking for 6 sine of 3t being less than 0. So then same process, sine of 3t has to be less than 0. I'm going to do sine of x has to be less than 0. Here we know that sine of x is going to be negative between pi and 2 pi. So x, start with pi, so pi has to be less than x, which has to be less than 2 pi. And then again, if we divide all those to get a t, or sorry, I guess we should replace that 3t, divide everything by 3. So between pi over 3 and 2 pi over 3, t, if t is between those two, then this thing is going to be negative. Okay, so it's going to the right between 0 and pi over 3. It's going to the left between, pi over 3 when it turns around. And then because we only care about till pi over 2, we don't actually care about till pi over, or 2 pi over 3. So this is going to be pi over 2, okay? And it does include that value because it's still going left at that point. It stopped at t equals 0 and t equals pi over 3. And we can confirm all of this graphically. So I've graphed this. So each tick is pi over 2. Okay, so it stopped at 0, meaning velocity is 0. It's going positive direction until here. So if this is pi over 2, this looks like pi over 3 to me. And then it stops again right at, so there's that stop at pi over 3, and then goes negative, and then it's still going negative at pi over 2, right? It's still going that negative direction here, so that's why we include that boundary. So stopped at 0, stopped at pi over 3, positive in between those two, and then between that stop and pi over 2, which is our end boundary, it's always going negative. Okay? So if you ever have like a multiplier in your sign, this is a really good way to do it. Substitute something else in and then solve for that x and then figure out what that would look like in terms of all the other stuff. Okay. So if we're talking about the particle's position when t equals 0, we know that position and velocity are related through an integral. So if we take the integral of this, so 6 sine 3t dt. So the 6 is going to come out. The integral of sine is cos. And remember, when we're doing the derivative of that, we'd have to use the chain rule, so we'd need a 1/3 out there. So if then we plug in a 0, we're going to have this thing. Oh, this should be a negative. Sorry, the integral of sine is negative cos. So let's add that negative in there. It's going to be negative 2 cos of 3 times 0. Cos of 0 is a 1. So the position at time equals 0 is negative 2. If we want to know the position at pi over 2, we're going to do the same thing and just plug in a pi over 2. So we can just use this, so 2 cos 3 times pi over 2. So negative 2. Pi over 2 is, or 3 pi over 2 is down here. So the cos of that is a 0. So then that is, oops, that's not negative 2. That is 0. Okay, so it was to the left, now it's in the middle, right? Which makes sense because in between these two things, it was moving to the right more than it was moving to the left. So what's the displacement of the particle in that interval? It would go from negative 2 to 0. So it's moved 2 in the positive direction, right? 0 minus negative 2. So what is the total distance traveled by the particle in the interval 0 to pi over 2? Shown as a Riemann sum. So that is the sum of the rectangles. So the velocity at some time times how many little rectangles we split it into. Okay, so that would be the Riemann sum, the sum of all of these little rectangles where we've got VT and we've got the change in t, and we're adding all them up. Rewrite as a definite integral, so that would be the sum from 0 to pi over 2 of the integral. And if you think about what we did up here, we took the top position, pi over 2, subtracted the bottom position, and we got that change, we got that displacement. And then evaluate the integral. This should be the exact same. So we already figured out that the integral of this is 6 times negative 1/3 cos 3t. We're going to evaluate that from 0 to pi over 2. So it's going to be a negative 2 cos of 3t from 0 to pi over 2. So negative 2 cos at pi over 2. Sorry, 3 pi over 2 minus negative 2 cos of 3 times 0. So that's going to give us the negative 2 times 0 minus 1. And there is that 2. Same deal as what we got up here. Okay, so stuff that we're familiar with, just kind of wrapping it all up together in all of the different ways that we've talked about it so far. So a couple more examples. Use each of the graphs to answer the following questions. So how far did the object travel in the first 3 seconds? So if this is speed, this is a velocity. So if we're trying to figure out displacement, we're adding up the area under there. Okay, so the area is just 1/2 of the base times the height. So instead of writing an integral for this, we don't know the equation, we can just use our area scale. So 1/2 times base is 3, height is 6. So 18 divided by 2 is 9. And because this is meters per second and second, we know that the distance or that displacement must be also in meters. Okay, what's the displacement of the object in the interval 2 to 7? Okay, so this time it's from here to there. So that's a little bit trickier, right, as far as areas. So I'm going to split it into, we've got a rectangle there, then we can do another rectangle there, and then this triangle. So again, area is going to be equal to, we're going to do base times height of this one. So base is 3, and then height is 8 plus base times height of this one. So base is 2, height is 4, and then plus the area of the triangle. So base is 2, height is 4. So you can just split it up into nice easy shapes that we can figure out. So we've got 24 plus 8 plus 4. So 28 plus 8 is 36 meters. Okay, so kind of a physics throwback, but now when it's harder stuff, we can also do it. For this graph, what's the total distance traveled by the object on the interval 1 to 6? So the total distance is going to be the absolute values. And this graph is nice because it gives us 5 units of area above the x-axis and 4 units of area below the x-axis. We don't even have to calculate the areas. Not that it would be hard. But so because it's the total distance, it wants to know, okay, it went 5 to the right plus negative 4 to the left, but we're absolute valuing both of those. So 5 plus 4, so 9. And it doesn't give us like a meter or second, so we're going to just call it units. If it asks us about displacement, remember displacement is overall, where is it ending up? So if it went 5 to the right and 4 to the left, that's 5 minus 4, so we end up 1 unit right. be our final answer there. Right, because 5 is our positive, 4 is our negative. Okay, couple other applications we can do. So these ones are going to be harder to actually add up the area. So the rate at which your home uses electricity is measured in kilowatts. So if you remember back to Science 9, kilowatt hours, the rate you're charged for 1 kilowatt for 1 hour is called the kilowatt hour. Suppose the rate of consumption in your home is given by C at T is 3.9 minus 2.4 sine of pi T over 12, where C at T is the number of kilowatts and T is the number of hours past midnight. So what does this graph look like? So I'm gonna I graphed this and I'll sketch what comes up. So this is time in hours, and I'm just gonna put like 12 and 24 as my base here. And then we do know that this is our D value, this is our A value. So the middle of our graph is going to be at 3.9, and then our amplitude is going to be at 2.4. So at the lowest it's going to be is 1.5, and the highest it's going to be is 6.3. Right, because if we add 2.4, subtract 2.4. Because this is a negative A value and it's a sine graph, we know it's starting on the midline. There's no C value. It hasn't shifted left, right. So it's starting on that midline, and because it's negative, it's going down, right? And then we need to think about what their period is looking like. So period is 2 pi over our B value. So 2 pi divided by, our B value here is pi over 12. So pi over 12. My pi's cancel. 2 divided by 12 is the same as 2 times 12. And we get 24. So our period is 24 hours. So this sine graph is gonna, it's gonna end there. So then halfway through the period has to come up through the midline there, and then like that. So without actually graphing it, we can think through what this graph looks like from our Math 30 skills. Now this kind of makes sense, because if this is electricity consumption, this is midnight, you're not consuming a ton of electricity when your family's asleep. This is like your little brother staying up gaming, or older brother, I suppose. Staying up gaming, everybody's in bed, the heat's still going, like you're still using some electricity, that kind of stuff, like maybe somebody gets up, turns the light on, but then around like 6 a.m. things start happening. This is like 6 p.m., right? This is noon, this is 6 p.m. This is like dinner time. People are doing laundry. Everything's happening. The dishwasher's on, right? So that makes sense. So that's what our graph looks like. And what we actually want to answer is what the consumption for one day measured in kilowatt hours. So what is that consumption? Okay, so essentially we're doing the sum of all these little rectangles, right? So we're doing the sum of the consumption at time k times that delta t, right? Or we could write it as an integral. So from 0 to 24 hours, what is the sum of this thing? So we're going to just use our antiderivative skills to be able to do this. So the integral of 3.9 is going to be 3.9 times t. The integral of this, we're going to bring that negative 2.4 out in front and then worry about it. So the integral of sine is negative cos. Oh, I should have left some room. Of that pi t over 12. And then that's going to have to multiply with this would come out and multiply. So we're going to have to flip it so that it kind of goes away. It's It's going to be multiplied with pi over 12. And then we're going to evaluate that whole thing from 0 to 24. Okay, so when we simplify this thing, we're going to have 3.9 times 24. And then this is going to turn into a plus, right? Plus, and this whole thing is going to get multiplied. So 2.4 times 12 divided by pi. I'm just going to leave it as 2.4 times 12 divided by pi, because this whole thing I'm just going to plug into my calculator. And then cos of pi times 24 over 12. So there's my 24 plugged in, and then minus my 0 plugged in. So 3.9 times 0 plus 2.4 times 0 over pi cos pi times 0 over 12. So, like this we could do just off of our unit circle. 24 divided by 12 is just 2 pi, right? So this is unit circle, but this stuff does get complicated. So I'm just going to plug it all into my calculator. So I get 107.767 minus 9.167. So I get 93.6 kilowatt hours. Okay. And then you can always check with your function integration on your calculator, or you could graph this and do the second calc integration function. Okay. So our last example is Hooke's law is given by the equation f of x equals k times x. So this is from physics and is used to measure the force it takes to stretch a spring beyond its natural length. The value for K measured in newtons per meter is called the spring constant and varies from spring to spring. Okay, so from physics 20, we can remember, I don't know what people would do if they didn't take physics 20 in calculus. It's all physics 20 stuff, so I'm glad you guys did. So remember from physics 20 that if you have a force and a distance, your slope of that line is your spring constant, right? Because that slope is newtons per meter, so your rise is newtons, your run is meters. So this is your force, and then this is your distance, right? So that's how those things are related. So a spring has a natural length of 18 meters and a force of 20 newtons is required to stretch and hold the spring to a length of 24 meters. What's the work required to stretch a spring from a length of 21 meters to a length of 26 meters? Okay, so let's think about this. We're going to start with a spring with a natural length of 18 meters and there's some sort of mass on it. Okay. So that is 18 meters. Then we need to get that out to 24 meters. So F at x is equal to kx. And to get it out to 24 meters, it takes 20 newtons. So if my force to get to x is 20, and my x, that means there's a distance here, there's a stretch of 6. Okay, so that's how we can solve for k. So k is equal to 20 over 6, which is the same as 10 over 3, and we know that's newtons per meter. Okay, so that's kind of our first bit of information we can solve for k. Then, if we know this equation, if we put k in, represents that spring. Remember how work is the area under that curve. So again, that's a physics 20 thing. I have told you, work as far as integral, or the relationship between this graph and an integral. Work is the integral. It's the area under that force. Okay, so we're going to do the integral from 21 to 26 of, I forgot the room for the over 3. 10 over 3 x dx. Oh wait, we don't want 21 to 26. We have to think about this a little bit more. So if 18s are normal and we want to get from 21 to 26, 21 is actually a stretch of 3 meters, and then 26 is a stretch of 8 meters. So it should go from 3 to 8, not 21 to 26. But that's an easy thing that they can trick you with, because I just got tricked until I looked at my notes. So that 10 over 3 is going to pull out, and then the integral of x dx, that's a really easy, nice one. It's going to be 1/2 x squared, and we're evaluating that. I'm so used to being from 0 to something, from 3 to 8. So 10 over 6 times 8 squared minus 10 over 6 times 3 squared. So 10 over 6, we can simplify all this. We're going to get 5 over 3. 8 squared minus 3 squared is 55. This is 275 over 3. And then if you remember work should always be measured in joules. Okay, if you did this as a decimal, that's also okay. But yeah, the area under a force graph is always going to be work. Because remember, work equals force times another distance. So the force, if you think about like a little baby rectangle in there, force is that y coordinate, distance is that x coordinate. So if you add up all of that, you're getting the area under a curve and getting work. Okay, so there's a few different applications. Here's some practice of all of that. And if you have any questions, let me know. We won't do a review Q&A on this until Thursday. But if you're really stuck on anything, send me an email and we can set something up. Okay.